Well, I guess I kept you in suspense there of what that false statement meant. Sorry about that. I didn't mean to. So our section 6.2 continued again here. Our false statement from example number 12 leads us to the conclusion that the solution for this system is a null set. In other words, what we have going on here is two parallel lines. Remember that when lines are equidistant at all points, they'll never touch and they'll never cross, which means there's no place that they'll intersect and have a solution at the same time. All right, now let's look at example number 13 and see what happens with example number 13. Yes, and there might be some funny business happen with this example as well. So in this one, gosh, I don't want to mess with that. It's got a fraction in it, so let's not. Let's go ahead and solve the second equation that we see there, x minus 8y equals 4. Let's solve that equation for x because, again, that numeric coefficient of x is 1, so it should make it easy to solve for. So I'm going to go ahead and I'm going to add 8y to both sides of this equation, and then I'm going to have x is equal to 8y plus 4. Now that expression for x I can substitute into the other equation. So now I have this 1/4 times my x value, and I'm just going to put big parentheses for there, minus 2y is equal to 1. Now you might think, oh gosh, that's going to be really hard. It's got a fraction. Don't worry about it. This one works out okay. You'll see how that it works out in a second. And put that value, 8y plus 4, in there for the x, and then we're going to distribute this. Well, multiplication by 1/4 is actually division by 4, right? So this says 8 divided by 4, which is 2 y's, plus 4 divided by 4, which is 1, minus 2y, which is equal to 1. And as I said, funny business happens again, right? Because when we go to combine the like terms here and here, what we see is 2y and negative 2y is 0. So what we end up with is 1 equals 1, which this time around is a true statement. And anytime we end up with a true statement in this process, that's telling us that we have infinite solutions. These lines are the exact same lines, and therefore everything that solves one solves the other. And remember, I told you that it was okay to just write infinite solutions. A lot of books will make you write an equation for the lines and put it in set builder notation, but we're just going to go ahead and say that it's infinite solutions. All right, so example number 14. Oh my, fractions. Well, fractions are where the substitution method does break down, but don't forget you can clear. So let's clear these two equations independently of one another. So I'm going to clear this one by multiplying through by the LCD 6, and don't forget every single term by 6. So 6 divided by 3 is 2, 2 times x, plus 6 divided by 6, which is 1 times y, 1y, and 1 times 6. Down here, I'm going to multiply through by 4. So 4 here, here, and here. And 2 goes into 4 2 times, so we have 2x. And then 4 goes into 4 once, and so we have 1y. And then we have 0 times anything, which is 0. And so you see this one, if I solve this second equation here for y, it's going to be really super easy solution. So we have y moving over to the other side, and so I have y is equal to 2x. Remember the reflexive property of equality, which means that we can flip those around and it's okay. So now I have an expression for y to take and put into the other equation. So now in step number 2, I'm going to have 2x plus 2x, because that's my y value, is equal to 6. And then we have 4x is equal to 6. And then multiplying by the reciprocal, which looks like division because it is, and then simplifying this one, so we get 3 here when we divide by 2, and when we divide by 2 here, we get 2 here, so we get 3/2 for this, and that's our x value. Now I never promised, just because we cleared the fractions, that we would actually end up with an equation that didn't have an answer that was a fraction. So now I can take this 3